Hey everyone, welcome back to the number system and conversion series. And this video focuses on hexadecimal to binary conversion. So let's get started. What we will cover in this video: first, the 4-bit binary equivalent of any given hexa number. We will solve some examples which will include both the fraction part as well as the whole number part, and then how to manually cross check or verify your answer. So what all information I should have to understand these type of conversions? First of all, hexadecimal number system is base 16 number system, and it has got values from 0 to 9 and 6 alphabetic characters from A to F. Then these are the corresponding decimal equivalent of any given hexadecimal digit. So F in hexa is equivalent to value 15 in decimal number system. But what is of prime importance that we must all know is the binary equivalent of given hexadecimal number. Binary number system is basically a base 2 number system, and it has bits 0 and 1. So how to write that set of information, or that those bits which will represent some hexadecimal digit? So every hexa digit is represented using 4-bit binary equivalent. When you write the normal binary sequence, you write like this: single bit for 0 and 1, then 2 bits for 2 and 3, and 3 bits for 4. So, but when we are writing the binary pattern of any given hexadecimal number, it has to be a 4-bit number. So 0 will not be written only 0, it will be written as 4 bits. 1, this is the basic code, but it will be used framed using 4 bits. Here 3 bits are already there, and one more bit will be added. Here 2 bits will be added. So this gives me 4-bit code. So why it is always 4? Because 16 is the base of hexadecimal number system. It is also the power of 2. Which power gives me the value 16? That is 4. So every hexa digit is represented using this 4-bit binary code. So see, 0, that is written using 4 bits. So any hexa number will have corresponding 4-bit pattern. But how to quickly recreate this entire chart? And if I am given as the value of F, I should be able to quickly recreate, get the binary code rather than making this entire chart. So we will use this method, sum of weight method. Because it's a binary number system and there are 4 bits, so these are the positions of that binary number. And that calculates to 1, 2, 4, 8. And what sum of weight method says? Suppose if I have to find the value 9 in hexa and I have to find out its decimal binary equivalent, then what I will do is I'll write this 1, 2, 4, 8. This is my value 9 in hexa. See which weights add up to give me value 9. So 8 plus 1 is 9. Mark those bits with 1, and the weights which do not contribute in the addition, mark them with 0. So let's recreate this entire chart quickly over here. So 0, so it will be, this is basic code of in binary, but 0 will be written using 4 bits. So you can write like this: 1, 2, 4, 8, right? And then this is 1, this is 2. Just see, you have to take care of these weights. Then 3, 2 plus 1 is 3. 4, so this is 4. 5, 4 plus 1 is 5. So mark weight 4 with 1 and weight 1 with 1 bit, and rest of the bits will be 0. 4 plus 2 is 6. 7, 4 plus 2 plus 1 is 7. So this weight 8 will be 0, rest of the bits will be 1. 8, this is 8. 9, 8 plus 1 is 9. Again write here 1, 2, 4, 8. Now A is equivalent to 10 in decimal. So 8 plus 2 will give me 10. B is equivalent to 11. So 8 plus 2 plus 1, they will give me 11. Now C is equivalent to 12 in decimal. So 8 plus 2, 8 plus 4 will give me 12, and rest of the bits will be 0. D is equivalent to 13. So which bits will add up? 8 plus 4 plus 1. So 1, 1, 0, and 1. E is equivalent to 14 and F is equivalent to 15. Now just count which weights will give me 14. 8 plus 4 plus 2. And this 8 plus 4 plus 2 plus 1 will give me 15. So it is 1, 1, 1, 1. All bits will be 1. Now I'll erase this entire chart and we will just randomly pick any hexa number and write its binary corresponding binary code. Suppose I write for D. So D is what? 13. Write 1, 2, 4, 8 on the top. So 8, 9, 10, 11, 12 plus 1 gives me 13. So you can quickly derive the binary pattern. Now suppose I give you random binary pattern 0, 1, 0, 1. Identify which hexa digit it will represent. So write 1, 2, 4, 8. And then see which bits correspond to 1. Add those weights. So 4 plus 1 is 5. So it is this, right? So this information is must for having the our so let me go into previous slide, and this information is must for this type of conversion. And there should be no mistake over here because one wrong pattern will give you wrong answer. Now let us see what are the rules to convert the hexadecimal to binary. See, this conversion is very easy and straightforward. Just replace each hexa digit with corresponding 4-bit binary equivalent. Suppose you are given this number 3E1F5 in hexa. So how many digits are there? 1, 2, 3, 4, 5. 5 hexa digits. So you have to replace each of these hexa digit in sequence, each with its corresponding 4-bit binary equivalent. So let's solve some examples. And we will also learn how to verify them. But first, let's look at our, first let's get into our copy and let's see this number 3E 3E156. This is a hexa number and I have to find out its binary equivalent, right? So we'll write 3, then E, then 1, then 5, and then 6. In case you forget, just write that pattern 1, 2, 4, 8. Right? Now you have to write the binary pattern. So this is the binary pattern for 3. If you write in this manner, naturally you will not commit the mistake. 1 is this, 5 is this, 4 plus 1 is 5, and 6 is 4 plus 2 is 6. Now E is equivalent to 14 in decimal and 14, so 8 plus 4 plus 2 will give me 14, right? So you're getting a long binary string. See, one hexa digit represented by 4 bits. Now how many hexa digits are there in the question? 5, so you must get 20 bits. So that is also one way to cross check. So 4 to the 8, 4 to the 12, 4 4 the 16, 4 5 the 20 bits. Now I'll just mark this section so that you can understand where I'm writing what. So now we'll just first combine the string, then 1 1 1 0, then I'll write this 0 0 0 1, then I'm writing this part 0 1 0 1 and 0 1 1 0. So I'll just write it with just a little rough work I'll do over here. This is 3 and this is E and this is 1 and this is the code of 5 and this is code of 6. Now I know that I have not omitted out any bit. Now what you can do is, because this is a whole number part, these 2 bits which lie on the extreme left, if they are zeros, you can just omit out those bits. Any 0 which is in between the number or on the right should not be omitted in case of whole number, but any extra zeros on the left side, extreme left, can be dropped out. So this is the answer you get. Let's first cross check in our calculator and then we will understand the manual method. Let me check this hex up code, and now let me write the value 3E156 and see, this is the answer you get. This one, right? All you can see that clear pattern of 4 bits each. So binary strings will get long. You have to exercise care when you're writing your answer. Do cross check before you finalize your answer. Now let's take this question 3a.c and then we will understand how to verify it. So this has got both the fraction part and the whole number part. So whole number is 3a. Then put your radix point and this is your fraction part. So now you write down their binary codes 1248. So that was why that rule said each digit, right? So let us write their codes. 3 is 0, 0, 2 plus 1 is 3. A is 10 and 8 plus 2 is 10. Then C is 12, 8, 9, 10, 11, 12. Let me get the answer 0, 0, 1, 1. Then let me write this part 1, 0, 1, 0 dot. Always put that fraction point, that binary point at the correct place to get the correct answer. So this is my binary code. Now, if you see here, in case of the whole number part, there are 2 extra zeros on the extreme left. These leading zeros can be omitted. Similarly, for the fraction part, these trailing zeros which lie on the extreme right, they can be dropped out in the final answer. So we will get 1, 1, 1, 0, 1, 0 dot 1, 1. So this is my answer. Now, one drawback of this programmer calculator is that it will give me the code for the whole number part, but it doesn't support the fraction number. So if I write 3a, it's giving me the value this 00101010, this part. It doesn't support the fraction part. So before we manually verify it, let's check this number, double F, find out its binary equivalent. So 2 digits. So 1, 2, 4, 8. F is equivalent to value 15. So all bits will be 1. So no, there is no extra zero. There are no zeros uh, on the left edge. So this is your final answer. Right? Now you must be. It will be very interesting to know whether my this answer is correct or not. This was my answer. Right? Let's verify the result. Naturally, you can't carry your calculator everywhere, and I must know the manual verification method. Generally, you don't have to perform the verification every time, but if you are asked, you must know, you must be damn sure that your answer is correct. So if in case you're curious to know how to manually verify it, so let's see that. Let me write it in this way. Right? Now let us see how will I verify it. If you check in your calculator, I have written this value, hexa value 3a. And this is this corresponding binary code. But apart from that, it is also showing me this decimal number 58. That means if I convert hexa number 3a into its decimal equivalent, I'll get 58. And if I convert this binary string into decimal, again, I will get 58. So Simple rule is you have to convert the answer and the given question, that value, into decimal equivalent. So let's see how to do that. First, let's work out with our integer portion, right? So let me mark this over here. Our integer portion has value 3a, right? I want to convert it into its decimal equivalent. So how many things you have to do? Then you will also convert dot c into its decimal equivalent. Then what was the binary code of 3a? That was 111, then 010. You will convert this code also into decimal equivalent. And what was our binary code that we received? Dot 11. You will also convert this into decimal equivalent. And answer of both these, whole number part, question part, as well as the answer part, they should be, decimal equivalent should be same. And similar is the case for this. Whatever answer I get here should be identical to the answer that you get in this 0.11, and point C will give you the same answer back. If there is a difference in the answer, that means there somewhere we have committed the mistake. So I will do one question quickly for you. So first let me start with this 3a. If you are not familiar with hexadecimal to decimal conversion, then I have created a video on it, and you can check the description, its link in the description box. So what it says is 3a. So 3 into 16 to the power of 1 plus a into 16 to the power of 2. A is 10. Sorry, I went wrong over here. Let me correct this. This is 16 to the power of 0. Right? Now you can just do your normal addition and first do the multiplication. So this become 10, this become 48, and your answer is 58. So if you see here in the calculator also, 3a was giving me this answer 58. But question arises, if I convert this binary pattern, do I get the same answer? So here this is 58, right? This was the value that was given, and this was our answer of whole number part. So remember, you have to perform it separately. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and 2 to the power of 5. These two bits will get dropped because they are 0. We will just add up those bits where we are having 1. So this become 2, and this become 8, 16, and 32. Just add them, 32 plus 16 plus 8 plus 2. And answer you get is 58 in decimal. See, your answer is same. 3a, it gave me a result 58, and when I convert this string, this was also giving me 58. So my this answer is this binary pattern is correct. So my this number, this whole number part given in my question, and my whole number part which I received in the answer, they are correct. So whatever pattern I wrote over here is correct. Okay, let's see that dot c part. Here I'm having dot c, and what was the value that you were getting? That is dot 1, right? So this will get into, we will c is equivalent to 12, 12 into 16 to the power of minus 1. So if you make all the calculations, you can just check out. So this will become 12 divided by 16, and answer that you will get is 0.75 in decimal. Now let us convert this 0.11. So 1 into 2 plus 1 into 2. Because it's a fractional number, so negative weights. So this become 1 into 1 by 2 plus 1 into 1 by 4. So 1 by 2 plus 1 by and you will get the answer 0.5 plus 0.25, and you get 5 and 7. So this is the answer you are getting. Answer is identical. That means our question was okay, right? So what we did, I'll just revise once. This was the original number and this was our answer. In order to find out, simple rule is whatever question is given to you and whatever answer you get, just find it out their decimal equivalent, and uh, that answer should match, right? So 3a converted into decimal is 58, and its binary equivalent that we got was 111010, and we are also getting 50. Then because we have fraction part, so we will perform the separate calculation for that. We get 0.75 for dot c, and dot c is equivalent to dot 11 in binary, and it is answer is same. So decimal quantity will remain same. So this number has to be taken care of, whatever number is given. Now if I ask you ff, one thing which you can do on your own, if I take this ff number, its binary code that we got was this, and this is its decimal equivalent 255. That means if you want to cross check this number, just write ff, convert it into its decimal equivalent, and write this answer because there is no fraction part over here. Convert this also into its decimal equivalent. For having performed all the calculations, what answer you should get? 255 in both the cases, right? So this is something which you can do on your own, right? So let's see one animated example. This is the given number 2e1.fe. So it has the integer portion and fraction portion. We will replace each hexadigit with its corresponding 4-bit binary equivalent. So these are the codes for 2e, 1, f, and e. You have to just follow that principle 1, 2, 4, 8. Combine all the bits, and here we have dropped out these leading bits from the these leading zeros from the fraction part. Sorry, from the whole number part. So this is our information. Even if you don't omit out, like I have not omitted this zero on the extreme right, answer will be okay. So we will wind up with this session. Thank you for viewing. Kindly subscribe for the to stay tuned with the more upcoming videos, and you can also share it with your friends. So I'll meet you in the next video. Till then, thank you, take care, and bye bye.